Okay, in this lesson, this is a module 2 lesson under unit 2, right? That it speaks about electronics, and in a sense, with this, it's just going to talk about how a specific device works mainly, and that's what we call a semiconductor device, right? Because right now, when we think about electronics on a whole, right, we are literally using what we call semiconductors. And what we have come to understand is that semiconductors are really ideal for whenever we are, creating electronic components and so forth because of the nature of how it works, right? Normally, we'll use conductors whenever we want electricity to flow, but conductors can be a little bit too risky when it comes down to electricity, right? Because conductors will always allow electricity to flow. Semiconductors will allow electricity to flow based on certain conditions. And of course, we know that insulator does not allow electricity to flow so easily, or it really does not, because of some things that we'll be looking at, talking about the band gap and all of those things. So we just want to start it out by just making mention of semiconductors, right? One of the things that has revolutionized society today is what we call semiconductors. And what we're looking at here, these chips that you're looking at that are used in your computers or in your motherboards and all of those things, even a very LED, they are really made using semiconductor materials. And if you know your periodic table well, right, your periodic table is divided into metals, non-metals, gases and all of those things. And there's a section in your periodic table that we classify those as being, semiconductors per se, like a group 4 element. Those would be classified as semiconductors. So a silicon, right, a germanium, those things that fall within, possibly a carbon, but we don't really use carbon mainly. So group 4 elements are really semiconductors because they lie in between metals and non-metals, right? So in a sense, all of those elements really, most of them, right, tend to be, ideal for being a semiconductor. And as the word suggests, semiconductor, which means that it has the possibility of conducting electricity, and then it also has the ability of not conducting electricity at some point. Now, I'm pretty sure you have heard about, I think, such as the Silicon Valley and, that kind of thing. When you talk about the Silicon Valley, it's really about using silicon as the main semiconductor, um, material, right? That is used to generate these different chips and so forth, right? The Silicon Valley, it's just all about technology and electronics. You understand? And you can do some research about that, right? So the term Silicon Valley just speaks to the fact that most of the ICT chips that are processed and are the processors chip, right? Those are really built based on how you properly utilize these silicon elements. All right. As we know, semiconductors can be defined as materials which lies between a good conductor and an insulator. Here are some examples that you should be acquainted with. You have carbon, as I would have stated, silicon, germanium, right, and so forth. The unique thing about these electrons, or not electrons rather, but these elements is that they are found in group 4, which means that they have 4 electrons on its outer shell. So, can you just imagine you considering, right, I think such as carbon, right, then you know that you will have 2 electrons on the first shell, then you have the remaining on the other shell, on the last shell, right? So this speaks to the electronic configuration, and this is what we're really going to utilize. You understand, to pretty much change the ability of the semiconductor per se, and you're going to see it at some point. But I just want you to know that these are elements that generally have 4 electrons on its outer shell, and those 4 electrons are going to be like the real thing here that will be what you call it now, will be used to explain the whole process. All right, so just pay attention to that. Now, a part of this lesson, we ought to be able to can understand, and if you check your syllabus, all of these information that we talk about here are stuff that the syllabus requires for us to make mention of. And it asks us to talk about what we call an intrinsic semiconductors. All right. Now, these are pretty much the same, what you carbon, the same, the same carbon, the same silicon, the same germanium. But in this case, when we say intrinsic, intrinsic just speaks to the pureness of the element, right? Meaning that it's just completely silicon. So as you can see right here, if I were to have a lot of silicon combined together, then this would speak to being an intrinsic semiconductor, right? Now it says that combination intrinsic semiconductors exist as such, where you have several of them conducting. It says um, another type of intrinsic semiconductor though is what we call cadmium sulfide, right? That are lead sulfide, those also are classified as intrinsic semiconductor. So it's not just a pure silicon or germanium, but a combination can also be an intrinsic semiconductor material. And that is just when you have pure elements. So you'll have pure lead, you'll have pure sulfide combined together, right? No other stuff, right? You're going to hear us talking about impurities very soon when we look at the next type of semiconductor, all right? Now, one other thing about semiconductors is that its electrical property, right, which we're going to talk about resistance. Because what you understand is that, when we talk about conductors, it has a lot to do with our semiconductor. It has a lot to do with the resistance, with opposition to the flow of charge, and so forth. Now, whenever temperature is increased in a semiconductor material, we find that the resistance, right, is going to decrease. So this is kind of like the reason why, calcium sulfide and lead sulfide are classified as, you know, intrinsic semiconductors, because they would pretty much behave as how a pure silicon behaves. So pure silicon would work to say that, if I increase the temperature, what that is going to do, it's going to reduce the resistance. And if you know anything about resistance, resistance is the opposition to the flow of charge. So if I increase the temperature in these elements here, what I'm really doing, I'm using the temperature or the heat to break the bonds, the covalent bonds in between here, thus causing electrons to can move from one level to another level, right? So that is what we're saying, that with increasing the temperature, it's going to reduce the resistance, and if you're reducing resistance, create the opportunity for charge to flow and for electricity to flow. All right, so that's kind of like the understanding here. We're going to look at this in greater depth, right? But the next type of semiconductors that we ought to know about is what we call extrinsic semiconductors. Now it says that metals tend to be good conductors of electricity because they have free electrons that can move easily between atoms, and electricity involves the flow of electrons. Now it says while silicon crystals look metallic, they are not in fact metals. It says all of the outer electrons in the crystals are involved in perfect covalent bonds, so they cannot move around. It says a pure silicon crystal is nearly an insulator, right? Very little electricity will flow through it. So we know that already, that with pure silicon, right? Because of how it is structured, right? All of those perfect covalent bonds and all of that, it does not allow electricity to flow. What we're getting into now is to understand how extrinsic semiconductor works, right? So based on what we just said a while ago, if you have pure silicon, the possibility of allowing electricity to flow is going to be limited because of the fact that the covalent bonds are there. There's no free electrons to allow electricity to flow, and we know that electricity needs electrons to flow. So in order for us now to can manipulate the semiconductors is by creating what we call extrinsic semiconductors. But in order for us to do that, we have to go through a process of what we call doping, right? Doping is a process of adding impurities to an intrinsic semiconductor. So let's imagine now that you have a pure silicon. Having that pure silicon, you will add an impurity to it. What we call impurity in this level is not dirt, but it's actually an other element, right? So if we take a different element from possibly group group 5 or group 3, then what you would see now is that that element will now enable the overall structure of the semiconductor to either have a free electron moving about inside of the lattice, right? Thus will create the ability for electricity to flow. All right, so it says that extrinsic semiconductors have added to them carefully controlled amount of impurities, and those impurities are atoms or molecules. Now it says that the impurities are added in parts per million, right, so as not to disturb the overall lattice of the host element, which would be the intrinsic semiconductor, such as a silicon or germanium. Now, when we do this, it says that this alteration causes a drastic change in the electrical property of the semiconductor. Now, it says that there are two extrinsic materials of immeasurably importance to the semiconductor device fabrication. And these two types of extrinsic materials that you will hear us talking about further on is what we call the N-type and the P-type materials. So through the process of doping, we are now able to create two specific types of extrinsic semiconductors. One which is going to be what we call the N-type material, and one that we're going to call a P-type material. Now, you're going to see how we create an N-type material, so to speak, which is in a sense an extrinsic semiconductor. We're going to show you how we do that using the process of doping. Because what you're going to see now is how we basically construct certain small chips that are used in the electrical industries and so forth. If you're going to do electronics, then you need to kind of have an idea of what's taking place. There's a whole lot of information, but you can definitely get it. So as I would have stated before, right, it says that both N-type and P-type material are formed by adding a predetermined number of impurity atoms to, let's just say for argument's sake, a silicon, because you can add it to different elements, but in this case we're using silicon. Now this is how the N-type material is created, right? And we have to know how it is created. Now the N-type material, let's just look at this right here. Here we have a diagram showing germanium, right? Germanium is obviously in group 4, and you have a lattice of several germanium, elements combining here together to form covalent bonds between themselves. Now, if I were to kick out one of the germanium elements, right, then there will be a void. If I were to go ahead and take an element that is in group 5, which has 5 valent electrons, which means that it has 5 outer electrons on its shell, and put it in between where I would have taken out that germanium, then what I would see obviously is that, you know, four of the electrons, four of the electrons from the group 5 helium, which is arsenic. So if I were to put in the arsenic right here, what the arsenic would do is going to bond itself with, it's going to share with those, you know, other what do you call it now? Those other, they're going to share their electrons between the germanium. And in that process of sharing those electrons, then there will be a single one that is left behind. So you see this one right here? Because arsenic is in group 5, then it means that it has 5 electrons. 4 is going to go towards the sharing of electrons. Then now there's going to be a void, which is pretty much not a void, but in a sense, there's going to be an extra electron. Now, you see this extra electron? This is what is going to cause electricity to flow in an N-type material. What this does is that it allows an excess of electrons to be in an N-type material. You understand? That is essentially what is taking place when you have an N-type material. Now it says that this remaining electron loosely bound to its parent antimony, or in other words, its atom, is relatively free to move within the newly formed N-type material. So, you know, I mean, it's not bound to anything, so it can freely move about its place, you know, and do whatever it wants. And we know that electricity needs free electrons to flow. So that now, this material is now an N-type material, because you would have used a group 5 element for one, and now you would essentially be saying that you have extra negative charge in an N-type material, because electrons are negatively charged. So because for that reason we can call it N-type material, because it has extra negatives, right? So we have extra negative. So that's one way we can refer to it as an N-type material, because it has extra electrons. So with all of that now, what we must understand is that the arsenic that was used, that element As, that is what we call a donor atom, because what it did basically was to donate 1 electron to the overall semiconductor material. You see what I'm saying? So that is what is taking place there, right? As it pertains to a p-type material, right? Nothing changes mainly about the process that is taking place. What we're essentially doing here is that rather than using a group 5 element, we're now going to use a group 3 element. Whenever we use a group 3 element, a specific group 3 element, which has 3 electrons on its outer shell, what you would see is that when you slap that electron, or you dope it, not electron, but if you dope that element inside of the lattice of the semiconductor, right, the pure intrinsic semiconductor, then what you're going to see is that 2 out of the 3 electrons are going to go into sharing, right, to create that covalent bond. And let me restructure that. All three electrons are going to share their electrons in a sense, right? All 3 is going to share their electrons. So what you're going to see happening now is that there's going to be a void. So it's like I need an extra electron in order to complete this process of bonding that is taking place right here, right? So all of my 3 electrons would have already taken up the space in terms of, you know, bonding covalently between the other germanium. But because now this element, which is indium, which is in group 3, right, what this is going to do is we're going to realize that we need an extra electron right here to pretty much complete the bond. And with that note, we can simply say, right? We can simply say that we have an excess of positive charge in a sense, right? It's not as easy as we might think. But what I'm getting at here is to show you that, you see, because there is a short of electrons, it now makes it seem as though that there is more positive charge inside of the overall material. And for that reason, we call it a p-type material, because what we're now saying is that because of the absence of that electron to fill this gap right here, to pretty much bond right here, we can then say that this thing is now positively charged rather than negatively charged. You understand? And for that reason, we can call this a p-type material. That's what I'm saying. So it says that the resulting vacancy. So because there is a void to be filled, right? You need an extra electron to complete the bond right here. So, and for that reason, we say that there's a hole. That hole, we treat that hole as a positive charge. If you get what I'm saying. So in some cases, you'll see a circle, right, to represent a hole. So a hole can be used to represent, you can use a hole, you can use a circle to represent a hole, which just shows that there's an absence of electron. And or we could have used, either a circle with a plus sign, that could also work, to show that there is a void, you understand, which just indicates that there's an absence of negative charge. But we treat it to say that because there's an absence of negative charge, then it means that there's more positives in there than negatives. That's pretty much what it has to say to us. You understand? It's important that we note something carefully about the majority and the minority carriers. Some cases you hear we talk about majority charge carriers and majority, minority charge carriers. Now, because an n-type material is negatively charged, which means that it has more electrons moving around in it, then we say that the majority carriers is going to be the electrons. You follow me? And then now, because you have more electrons, then it means that the minority charge carriers are going to be the holes, which are pretty much the positive charge. All right? So that's a thing you must remember. As it regards to the p-type material, because the p-type material has less electrons, right? Then we say that the minority charge carrier is going to be electrons. And of course, for the p-type material again, because you have an excess of holes because you don't have enough electrons, then we say that you have those holes will be the majority charge carriers. All right. Now we move on now, because this is where it gets very interesting, right? Because what the Silicon Valley has been doing, right, and those persons in the manufacturing industry, they have come to understand, or to, they have come to realize that if I were to take an n-type material, right, and a p-type material, and sandwich them together, right, meaning that you slab them together, right, you would now form what we call a PN junction diode, right? And this is a very critical, device that we have now created. So all I'm doing is that I know that I have two materials. I have one of these n-type, as you can see right here, and I have one of these p-type. When I take them and fuse them together, right, what you have observed just now is that in the n-type material, because they are negatively charged, they are more negatively charged, some of those negative charge are going to move across into the p-type material to bond with the positive charge. Good. Similarly, because you are moving, so two things are happening, right? Electrons are moving over this side to essentially bond with the holes that are here close to between the gap, right? Now, if electrons are moving from the n-type material, then it now creates what we call holes because there are less electrons in this side. So you now have a minority charge carrier of holes on this region. Now, one of the things that you're going to realize is that there is going to be what we call a region of depletion layer, right? Or you could hear we say the depletion layer or the depletion region. You see right in between here, so where you see it's being cordoned off, this is what we call the depletion region. And why we call it the depletion region is because the electrons here, right, pretty much have been bonding with the positive charge in this region. So what it does is that it creates a region where there is no free charge carriers. Remember now that your electrons on this side are your charge carriers, your holes on this side are your charge carriers. Now, if I were to basically remove electrons and put it on this side to pretty much, bond with the positive, negative and positive attract. So once you have both materials coming together, there will be a force of attraction where some electrons are going to move and bond together. So for that reason now, it creates a layer of depletion region, which just tells us that there is no free charge carriers within that region. So that is what happens when you take the p-type and the n-type material together. All right. So once you do this, you now form what we call a junction diode, right? And with the junction diode, it's a two-terminal semiconductor device where this side is going to be your, you can call this the positive terminal mainly. Well, now we're going to call this side the anode. The anode, as you can see from the diagram here, the anode. Then this side would basically be the cathode. Good, because that's the n-type, the n side. You could say that this side is the positive side and this side is the negative side as well, because of the whole fact that there are more positives on this side and there are more negatives on that side. Also, just remember this symbol right here. You see this symbol here? It's really important to show that that is what a PN junction diode looks like from that standpoint. So here's the p-type. You're taking a p-type material. You're going to bond it with an n-type material. Now, whenever you bond it with an n-type material, there is going to be a region or a junction. There's going to be a junction, what we call a depletion region, right? And remember we said now that the depletion region is that region where there are no free charge carriers within that region, right? So as you can see, if you read the information right here, it says that a depletion region is formed. So it says that electrons and holes migrate across the junction, right here, and it says now a depletion layer is formed, or depletion region. It says that a potential difference is set up across the depletion region. Because what you have to understand now, you see, because you have positives and negatives on one side, you also create a voltage, because if you know anything about charges, once you have positive charge on the one side and you have negative charge on one side, then you literally create a voltage. You literally create a potential difference. So there is a small voltage in between here that also needs to be that is going to be generated right here because of the whole migration of the positives and negative charge, right? So that is something very critical that we're going to look at. Another thing that we must be mindful of is the symbol for a diode. So this is the symbol, the schematic symbol. It's just like a triangle, like that, with a thing in front of it like this. Always remember that this side is the N side, or you can say that this is the N type material, or you can call it the cathode. Right, this side here is the anode, which is the positive side, so the P type. So that is something that you must remember, the symbol for a diode. You know, one of the things that you're going to see us talking about and using here is the whole fact that, you know, based on the orientation of the diode, right, that can now affect the way how it operates. That becomes critical when we look at the operation of it. Now, one of the beautiful things that I almost forget that, you know, I should be talking about here is that diodes, which is this device that we're looking at, it only permits current to flow in one direction, and it blocks the flow of current in the opposite direction. So this is one of the beautiful things about this device, right? It allows current to flow in only one direction. And when we look at alternating current in further lessons, then you will see how important this becomes to us. All right, this electronic diagram here, or this thing, is going to become very, very useful. So as I said, we form a PN junction by taking two extrinsic material, a P-type and an N-type material. Once we do that, a depletion region is formed, which means that electrons migrate from the N side to the P side to bond with the holes. And then, because those electrons are migrating, holes are generated within the N-type material. And because you have electrons on this side and you have holes on this side, it now creates a potential barrier or a potential difference. And you're going to hear us talking about a potential barrier very soon as well. So, yeah. Now, when it comes down to a PN junction diode, right, there are two main operation mode, right, or there are two main operating region, which we sometimes call biasing. Biasing is just talking about how the current is connected to the diode. So if you hear the terminology biasing, it's really talking about how the current is connected to the diode. All right. So one type of operation of a diode is when it can operate in what we call reverse bias operation. Then there's also another operation what we call forward biasing operation. Now, whenever the diode is in reverse bias, right, it means therefore that no current is allowed to flow through the diode, which means that it is not on. It is now acting as an open switch, right? It's now acting as an open switch. And if you know anything about switches, this would be a switch in electronics, right? This would be an open switch, right? So that's what happens whenever the thing is operating in reverse bias. Now, you must be able to can know when a diode is in reverse bias. How you know that? All right, this is the way how you're going to find out. Whenever the negative side of the battery or the negative side of the power source, right, is connected to the P-type, portion of the diode, right? Then now that simply makes it being operating in reverse bias. Also, obviously, the N-type material has to be connected to the positive terminal, right? And I'm going to show you in a diagram very soon, right? You know what this does in reverse bias, there is going to be an increase in the width of the junction, right? And let's if we look at a diagram to just clarify this or to just, show you what's happening here. So this is our power source, right? Here we have a battery right here, and we know that battery has two terminals, a negative and a positive terminal. Now, we just said a while ago, in order for the diode to be in reverse bias, the positive must be connecting to the N-type material. The negative side of the bias or the power source must be connected to the P-type material. Now it's easy to understand, but what you're going to see now is that there's going to be what we call a widening of the depletion layer. Now guys, the whole reason why that happens is all because of a simple thing that we call, attraction, right? Because what you must understand is that if you connect a positive to a side that has all negatives, then all the negatives is going to attract to the positives. Simple put. Similarly, if you connect a negative side to a positive side, then all what's going to happen is that all the positive is going to move towards the negative. Now, when that happens, it just creates a much wider depletion region. Why it creates a much wider depletion region? Because all of those positive charges that would have been here, right, they would have now moved themselves away from the region, away from the depletion region, thus making it harder for free electrons to flow across. All right. Similarly, when it comes down to the negative portion, electrons would have been here and so forth, right? But because you have a positive side that is attracting those electrons, then all of these electrons here are going to move over to this side, thus creating a very wide gap in between the junction of the diode, right? And when that happens, you do not have or you're not going to have what I would say now electrons to easily flow across the depletion region. The depletion region is depleted of charge carriers. So if you have a very wide area where there is no electrons that is available to flow across to allow electricity to flow, then clearly no electricity is going to flow, and that is when we say it's in reverse bias. Now note this circuit as well. This is showing you with the schematic diagram to show you when it's in reverse bias. Remember, I had said that this side is the cathode, right, which is the N side, N-type. So that is N-type. Then now this side right here is the positive side. So it means that this is now the anode, and this is the positive side, which is the P-type. So what we're seeing literally here is that the positive is connected to the negative, and whenever that happens, it's going to be in reverse bias. Similarly, the negative is connected towards the positive, so it's obviously in reverse bias here as well. All right. So that is very critical, and as I would have stated to you that whenever this happens, it acts as an open switch. So you're seeing the open switch right here, right, to say that no current is allowed to flow through it. Now I must mind you, right, before I talk about this graph, because this is a very important graph as well that we have to pay attention to, and we're going to talk about it a little bit. Right now, the next type of operation mode is what we call forward biasing. Now, forward biasing is simply put, it's the opposite of what happens in a reverse bias scenario. What you're going to do in a forward bias now is to connect the positive terminal to the positive or to the P-type material, right? And obviously connect the negative potential to the N-type material. And now what this will do, it's going to result in a decreasing of the PN junction width, right? And if I can find the diagram, right, this sort of like somewhat explains it in a sense. So this is now in what we call forward biasing. Whenever this diode is in forward biasing, it's now going to conduct, it's now going to allow electricity to flow. And it all lies within the whole aspect of attraction, right? Because what you're going, attraction and repulsion in this case, because what you're essentially going to see is that if I take the positive side, right, and I connect it to the positive side, then what it does, it's going to force, it's going to repel these positive charge or these positive holes, right, across to the N region. Similarly, right, with the negative side, with the negative terminal is going to force these charge carriers, right, to go towards the positive side. And of course, what we are also seeing is that because I now have electrons being forced to go across this region, which is the depletion region, it now tells me that I have electrons in the depletion region, which will now easily allow itself to pass over to the negative region, because there's always a force of attraction, between positives and negatives, and that's what it wants for electricity to flow. So if you are now able to force the electrons towards the positive side, right, then what it does, it's going to go across the gap, right, and essentially bond itself with the positive, thus creating a potential, difference, or allowing current to flow, basically. And as I said, now, because you now have electrons passing through the gap, right, the gap is no longer a depleted region because charges are now within it. So hence, it will now allow electricity to flow because you would have already forced these electrons into this negative region. This is how the diagram looks for when we have, this is very important, Don't neglect this diagram and how these things are structured, right, in terms of the biasing. Have to remember it. This is also another diagram to show it. This one is more sophisticated in showing you what is happening in terms of the movement of the charge, carriers, right? Yes. All right. And whenever we have a diode in forward bias, we say that it's a closed switch. So this right here is what we call a closed switch, which just tells us that current is flowing. All right. Now, guys, there's also a very important part as well that we must also make mention of. Have you remembered anything about what I said as it pertains to the depletion layer? Or when you take the N-type material and the P-type material and bring them together at first, what you essentially see happening is that there is a voltage that is set up or generated, right? If you check back this diagram here, this one right here, because of the whole fact that, electrons are on this side and holes are on this side, then it creates a potential difference. It creates a potential difference, or it creates a potential barrier. Before the diode can operate, right, it must overcome the potential barrier. You understand? It has to overcome that potential barrier. So what you will essentially see is that a portion of the power supply is going to be used to go against that potential barrier that has been already set up inside of the depletion region. You see what I'm saying? So we have to go against that. So a small voltage is going to be required at first before we can allow the diode to be completely in forward bias. And you're going to see it on the graph because that is important, right? That is important. But if you read the information on my slide here, then you will see what I'm talking about. It says that the application of forward biasing voltage on the junction diode results in the depletion layer becoming very thin and narrow, which represents a low impedance part. When we talk about low impedance, that is talking about low resistance, so there's less resistance to the flow of charge. So that's just another word to talk about resistance, impedance. And it says a low impedance path through the junction, thereby allowing high current to flow. It says that the point at which this sudden increase in current takes place is represented by the static IV characteristic curve above as the knee point. You see, when you look at this here, this diagram right here, this shows us the characteristic curve, this is how the diode operates in real life. This is what is taking place inside of it and everything. We must know how to look at this diagram. We must be able to can draw this sketch of the graph, right, to just explain what is happening. Now, on this positive region, on this side right here, this is when the diode is going to be in forward bias. You remember a while ago we just talked about the knee voltage or the knee point, right? And remember we talked about the fact that before the diode can be in forward bias, it needs a small voltage, right, to essentially allows it to start operating or to overcome the potential barrier, right, that is in between the gap. This is what is taking place. So with different semiconductors, if we're using silicon has a knee point or a knee voltage of 0.5 volts. So in essence, what we're saying is that silicon needs this amount of voltage first before it can turn on. So if the power source that you're using, if the battery that you're using does not have this amount of voltage in it, which is quite highly unlikely for that to happen. But if that voltage is being monitored and you don't have this amount of voltage flowing through the diode, then it's not going to turn on. It's not going to work. So it's like a condition. As we said, it's a characteristic curve. These are what defines it and tells it how it works. So if you're using a silicon diode, right, PN junction diode, and you want it to work in reverse, in forward bias, you must have enough voltage, which is this amount, to overcome the potential barrier. Because the potential barrier has a voltage inside of it that you must go against. If you don't go against that potential difference, right, that is in between the junction, right, then the diode is not going to turn on. But as soon as you now go through that, that potential barrier, then the diode is all yours. It's now going to conduct. And you're seeing here that it now starts to conduct like this, where, with an increase in voltage, more current is increasing and all of that, where the resistance is going to be constant for a period of time, right? So this portion just now tells us that the diode is now conducting and it's now in forward bias. Follow me? At this portion, it would not have been conducting as yet. But as soon as you overcome this small amount of voltage, then you will see that, it's now going to conduct. For germanium, you can see that the turning on voltage, which is what we call the potential barrier, is about 0.3 volts, which is more, it depends on what you want the device to do, but here, this is what it is. So in essence, if you wanted to use germanium and we want to plot it on the graph, if this is 0.7, then 0.3 would be somewhere here. So your graph would start going up like this for germanium because of the fact that it requires a much smaller voltage to overcome the potential barrier, right? I really hope it makes sense to you guys. Now, as it pertains to reverse bias, remember we said that a diode has two operations. It has forward bias and reverse bias. Now, in reverse bias, this is what is happening in terms of the curve, all right? This is what is happening. So whenever you're drawing your graph, it must look something like this, all right? What this is telling us, right, is that Because based on this, right, we're seeing that, you know, there's a very small current that is flowing, right? But with that, there is no with even with increasing voltage, right, up to a point, no, it will not be conducting, right? It will not be conducting, right, at this point because of the fact that there is not a variation in terms of the current and the voltage at the same time. Because in order for something to be really working in terms of electrically, right, there has to be, you know, a change in both things, right? So because current is constant here and voltage is increasing, it does not makes it work. You understand? But here we know there will be a point when the diode can actually work in it can actually work, right? At that point, we say that the diode has reached is what? It's breakdown voltage. So with a very high voltage, typically about, you know, negative 40 volts, like a very high voltage. If you were to use a very high voltage, right, passing through the diode, then you would essentially damage the diode. When you damage the diode, then it allows current to flow through it, which is what we call the breakdown voltage. So right in between this portion here that you see the graph now starts to shoot down, it now tells us that current is now flowing. Because at first, you know, no current, just a very, very, very small current is flowing. As you can see that the scale right here is microamps. Microamps is a very, very little current. So if very little current is flowing, then it means that there's a very high resistance. You understand? And that is what is taking place in the reverse bias. But there will be a point now when you will have so much voltage that the voltage is now going to break down the operation of the diode. It's basically going to destroy it. You understand? Because of the high voltage, and when that happens, you're going to see a very high current starting to flow through it, a very sharp current starting to flow, which just tells us that it's not allowing current to flow through it and it's going to conduct. You understand? So just remember that and be able to can label this to say that, you know, the Zener breakdown or the avalanche region. The avalanche region is just that portion of the graph where your voltage is at a level where it's now going to destroy the diode that is in the reverse bias operation. You understand me? Right? Remember now that you need a small voltage here, right? So let me just clear this up a little bit. So right here, you're seeing that the current is constant. The current is constant for this portion, which just shows you that that small current is not going to allow, you know, electricity to flow because you need enough charge. So remember that electricity our current is the rate of flow of charge. And if you only have a steady set amount of charge right here, then simply put, it's not going to allow the thing to work as how you want it to work. So up to a point where you now have enough voltage, which can be either 0.3 or 0.5, depending on the material you're using, then you're going to see a very sharp increase in terms of the graph, which just shows us now that, hey, a lot more current is flowing when my voltage is increasing, which speaks volume. That now enables to tell us that, you know, that the resistance is no longer that high because current is now flowing. All right. So all of this information is here for you to read and understand it. You see what I'm saying? A very important thing to also point out is to say that a diode is a non-linear device. From the based on how we see the graph here, this is not a linear graph. It's a curved graph just showing what is happening. All right. We ought to be able to can describe these things. Please I'm asking you to just, you know, pay attention to these things. This just breaks talk about what happens in the breakdown region. You can read that for yourself. All right. Now we reached a point, you see, where we are going to make use of you know what we call what we call rectification. Because what you see is that, remember we said that one of the main functions, and we must know this, one of the main functions for a diode is to allow electricity to flow in one direction, right? So with that being said, we're going to look at a process what we call a rectification, because the usefulness of a semiconductor diode is so good that you're going to be wowed when you hear this. All right, so we'll soon talk about it. Give me a second here. Yes. So it says that sometimes in life, it's necessary to do certain things. Also in physics, there are times when we need to do a thing what we call to convert alternating current into direct current. One other thing that we must understand is that you see electrical or electronic devices, they are very a peculiar set of devices. You understand? They are very, very, very technical, or very delicate, right? I am sure you would have watched videos about alternating current before, how it is really formed. Alternating current is really formed by having um, you know a generator, turning up and down and all of that and so forth. We looked at transformers and understanding that we can step up and step down a voltage, which is going to pretty much change how the pretty much change the voltage and all of that, and it creates alternating current and all of those things and so forth. So sometimes when that alternating current comes to your house, because one of the things you must remember is that JPS and those places, they are going to um, transmit current using alternating current, right, or alternating voltage, because of the advantages of it. Because alternating current can be easily step up and step down. Good. And when they do that as well, when they use alternating current, they can also reduce what we call power loss. And I think there's a lesson pertaining to that, which is totally different. But I just reiterating some stuff that as it pertains to alternating current and so forth. So when the alternating current comes to your home sometime, right, and you need to charge like your phone. Your phone is an electronic device. See? Now, your phone does not work off of alternating current. If your phone did work off of alternating current, then you would be seeing your phone light be flickering like this at all times. That's how you would see your phone light be flickering, because alternating current moves up and down. You understand? It alternates. So because we can't use alternating current with our devices, we have to use what we call direct current, which just flows in one direction. So imagine that this is your y-axis, current is on this side and time is on this side. It's moving in a direct path, it's straight, one direction. Alternating current, as you can imagine, it does not only move in one direction, it moves in both directions as time progresses, right? So we need to sometimes what we call rectify an alternating current. That's what I'm saying. We need to rectify it. Rectification is simply that process through which we convert an alternating current, cool, into a direct current using a PN junction diode. All right, and we're going to look at how we do that now. So as we can imagine, we said that diodes, right, allows current to flow in only one direction. So this means if I were to take an alternating current, right, and let's just for sake of argument, let me just draw a simple circuit. This is my diode, as you can imagine, and we must know to draw these things. And I have an alternating source. Now, this is a symbol for alternating current. It's just a circle with a wave in it that is alternating. Good. And then I'm going to have possibly maybe a light bulb. I don't know how do, yeah, this is a light bulb. This is how we draw a light bulb. Now, what you would see here is that once you connect an alternating power source, right, to the diode, what you're going to see that the diode is going to do is now going to only allow current to flow in one direction. It's going to only allow current to flow in one direction. Now, mind you, that in order for the diode to work, it must be in forward bias. It means that the positive alternating source must be connected to the positive end of the diode, and the negative end must be connected to the negative end of the power supply for it to be in forward bias. Now, clearly, what you see when it comes down to alternating current, what happens in alternating current is that the terminals are going to switch. So what I'm going to do now is to switch the terminals. This is what happens mainly in alternating current. The terminals then switch. So rather than having positive at this side, you now have negative. Now, whenever you have negative and positive connected in terms of the diode, then that is now in reverse bias. So it just tells us now that no current will be allowed to flow. Similarly, if the positive end is connected to the negative side of the diode, it's still going to be in reverse bias. You understand? And so that is the reason why we say that no current will be flowed through it if you have an alternating source. Because as I said before, that how the alternating current works is that at one point there will be positive current flowing through this part of the diode, right? And negative flowing through the next end of the diode. But then as time progresses, and that is going to change. So negative is now going to be on this side, and now positive is going to be on this side. That's how it really works. So as I would have been talking about, you know, the whole fact of current flowing, right, and so forth. Now, just a while ago, we said that. Let me just do a little bit of erasing here. We said a while ago, you see, that when the positive side of the alternating source is connected to the positive side of the diode, that's going to be in forward bias. So if I were to draw the resultant, right, or to draw the result graph, then what you would see is that the positive portion of the wave will be allowed to flow through the diode. But when the negative portion is reached now, so this is the negative part. This is the negative part, right? Which is now going to be negative and positive here. When that is now going towards the diode, then what you would see is that it's going to cut it off. It's going to cut it off, which in a sense means that it rectifies. It's going to rectify it. So there's a process of rectification, which is just cutting off the negative portion. So this portion right here is no longer there, because the diode does not allow that negative portion to flow through the diode. You understand? So it cuts off that point. So there's no current flowing now because the diode is in reverse bias. But as soon as the alternating current reaches this point again, the positive portion, then it's now going to allow the diode to work now. So guys, what you will be seeing is that the light bulb is now going to flick on, flick off, flick on, flick off. That is when you're using an alternating source. It's going to flick on. So when you think about your pepper lights and so forth, they are using some aspect of rectification in a sense, But not only that, they can be using other stuff, but you can create your own flicking on and flicking off type of light and so forth if you know what you're really doing, right? But this is the result of what is happening here. Now, you will see on my next slide that this is what we call half wave rectification, right? Half wave rectification. So at first, this would have been your input wave. This, as I would have shown you, this is what you started out with. That's your input signal. Good? But then now, because of the fact that you are rectifying the alternating current, right? Then this is now what you now produce. So you now produce a portion here in the, everything here is now in the positive region. And for that reason, we're trying to create alternating current. We're trying to create DC current, which means that DC current flows in one direction. So far, this is sort of like a direct current, but it is not completely a direct current because there is a gap in between, which simply means that no current is flowing. Cool? So because we have that gap, then we're not at the point of creating this. We want to create this where it is going straight across. At this point, it's not going straight across. It's going up, then coming back down and going back up like that. That is not completely direct current. We're close to it because it's now, the current is now flowing in one direction, which is the positive region, which is good. So we must know that half wave rectification is a process, right, of removing the negative portion of the input wave, input alternating wave, right? And as I would have stated, we must know the diagram as well, right? Okay, now we kind of move on a little bit now to another type of rectification process. So half wave rectification is just cutting off the negative portion of the graph, of the input graph, right? And leaving the positive region by itself. When it comes on to full wave rectification, this now is where it gets into, it's going to become a little bit more, complex per se, because it's now going to involve full knowledge and understanding of what is taking place, right? In full wave rectification, what we're essentially doing is that we're both rectifying, the negative portion as well, and also the positive portion. So what you're essentially going to do is to take the negative and make it become positive, right? That's what we're really doing in full wave rectification. Now, it says in order for us to achieve this, we must build what we call a bridge rectifier. And a bridge rectifier is constructed by using 4 diodes. Now, those diodes has to be structured in a particular way. If it does not structure that way, then chances are it's going to be wrong and wrong and wrong and wrong, right? It's a very tedious process to explain it, but we're going to look at it. This is what it looks like. We must know this diagram as well. We have to be able to can draw this. This is what we call a bridge rectifier, right? They are more simpler. When you move on to higher education, other than this, then you will see simpler circuits that you can use. You could use 2 simple diodes to do a full wave rectification, but for this level, we're just going to use the bridge rectifier because that's what is stated. So this is what it looks like. As you can see, guys, it almost looks like a bridge. So let's just look at this point. So 2 and 1, that would be like one bridge by itself. Then now 3 and 4, that's going to be like a bridge by itself. So it almost looks like a bridge. All right. So how these work now, guys? How it works is it works on a lot of concepts that we're going to look at. Right. So let me see here now. In order for us to take the negative portion, so what we're doing in full wave rectification, we're not cutting off the negative side. What we're doing, we're taking the negative and we're now going to flip it up to this part, right? So that's what we're essentially doing. Rather than cutting it off, we're taking it and we're flipping it over this side. So how we go about doing that is by obviously setting up our circuit as such with our AC input, starting off with positive and negative negative right here. Now let's look at it now, guys, because this is where it gets fun and very exciting. So here's our positive signal, or our positive voltage. That positive voltage is going to travel along this wire, and it's going to come to this junction. Now whenever it reaches this junction, it's obviously almost like a snail, and it wants to determine the better route, or the safest, not really the safest, but it wants to find out which path am I going to take to flow. Now remember that if you have positive going to negative in terms of the diode, then that is going to be reverse bias. And if something is in reverse bias, then this becomes an open switch. It becomes an open switch, so it does not allow current to flow. So whenever you have positive, because this positive signal is coming here, it's going to look and say, hey, will I go to 3 or will I go to 2? When it looks at 3, it's going to say, hey, 3, I can't go there because I'm now in reverse bias. So no current can flow. So the next best thing is for it to do is to flow through number 2 and say, hey, number 2, are you going to allow me to flow? Right? Then, because it's a positive signal, and we know that whenever positive is going towards this side, which is the positive side of the diode, then it now allows it to be in, it now allows it to be in forward bias. Okay? And if it's in forward bias, it's now going to allow electricity to flow. Now, when that electricity flows through number 2 diode and it comes to this point, mind you, that anytime you're drawing your diagram, your diodes have to be positioned like this. If they're not positioned like this, then dog will eat your supper. You understand? You have to look like this. If you look like this, then it depends on your own. You understand? When the positive signal reaches this point now, it reaches this point, it's going to do the same thing that it did at number 3. It's going to decide whether am I going to flow through number 4 diode, or am I going to go all the way through this resistor. So because we know that it's a positive signal and positive going towards the negative side of the diode, that's going to make it becomes an open switch, which is in reverse bias. So no current is going to flow now through that. So with that now being said, it means that the current only has this part to flow through, which is to go through the resistor, right? And when it goes through the resistor here, we can now collect the first portion of the rectification process. So if I were to go ahead and draw a graph, right, I can now see that this is essentially what I would have now, because I have those diodes that are in forward bias that are essentially blocking the negative portion. You understand? So that is what I have for the first part. And the current continues to flow all the way I'm not finished as yet though. So the current flow as all the way through the resistor. Then it comes to this point, it's going to jump over the wire. You have to also remember that the wire jumps over here, it does not connect. So this going over right here means that the wire jumps over this wire. Alright? And it comes all the way back to this end. Comes all the way back to this end. When it reaches here, because this number 3 is already in reverse bias, then no current is going to flow through it because it's already in reverse bias. So the next best thing is for it to do is to flow through this one, which is number 1. So number 1 now is going to be in forward bias, right? And then now that positive signal is going to come here. When it comes to this point, because number 4 is in reverse bias already, no current is going to flow through it irregardless. Then it's going to now continue back to the power source. Back to the power source. Alright? So this is just talking about the first positive portion. First positive portion. As you can imagine about alternating current, the thing is going to change, meaning that the biasing is going to change. So this is what we're now going to do. The biasing is going to change. So rather than having positive here and negative here, what we are going to do now is to put positive here and negative here. So now current now is going to flow from Q. So from Q, go all the way through this wire. It's going to come to this point. When it comes to this point, it's now a positive signal. It has to determine whether it wants to flow through 1 or it wants to flow through 4. Now, because if it flows through 1, it's going to be in reverse bias, so this now becomes an open switch. So no current is allowed to flow through that. Now an open switch. Then the only thing it can do is to flow through number 4. So it's flowing through number 4. When it reaches this point, it's now looking to see, can I flow through number 2? No, it won't flow through number 2 because it's a positive signal and our positive voltage. So it's now going to allow this to be in reverse bias, which is essentially an open switch. Then it continues now to the diode, right? So this is now when I take the negative portion and put it in between here. You understand? So that is now when I get this type of thing is what we call now full wave rectification. So that negative wave that, essentially that was here, we're now taking it and we're flipping it and bringing it up at this point to rectify. Then this signal continues. It continues all the way. It comes back to this point. It jumps over the wire. It comes to this point back here to this node. Then it's going to now want to think of where am I going to flow? Clearly can't flow through number 1. So it goes straight through number 3, right? So in a sense, another portion is now going to be here like this. And then when it reaches this junction now, it wants to determine where am I going to flow? Am I going to flow through 2? No, you can't go through 2 because 2 is already in reverse bias. So it then just continues and goes straight back to the power source. And that's how the cycle repeats itself. So now this is what we call full wave rectification, right? Or what we call a bridge rectifier, full wave rectification. This is the graph. Now, mind you, we're talking about voltage. So voltage is on this side, time is on this side, all right? And this is just showing us how the wave is progressing over time, all right? And as you can see now, this is now sort of almost looking like a direct current, basically, but there's still a point where it goes to 0, which tells us that it's not completely direct because it's going all the way to 0 here. And if it's going to 0, it means that no voltage is going through it and no current is flowing. So then we now have to fix that again. So in a sense, we are creating DC current, or we're rectifying AC current to get DC current. So we would have to get this whole full wave rectification and then do something else now to make it more easier. Now, what we're going to do now, right, is a process, or talk about a process of what we call smoothing. Right, smoothing is that process where we take that full wave rectification signal, right, and we sort of make it become, one that is more steady. You understand? So for us to do that, we have to take into consideration a capacitor. We have to take into consideration a capacitor, right, that will essentially fill that gap. A capacitor is a device that stores charges. Now, whenever the voltage is at 0, right, how the capacitors work is that the capacitor will store charge, right? It will constantly be storing charge up to a point when there is no voltage. So if there's no voltage, just like a regular backup unit, I don't know if you know what we call a backup unit, but something like, when you're at some internet cafes and light goes away, a backup unit chips in. to kind of keep the power going for a little while and all of that. How the backup unit jumps in, it jumps in based on the fact that if there's no voltage that is flowing from the regular source, then it now alerts the capacitor to now do a process of discharging. So what you're going to see happening here is that the diode is not the diode, but the capacitor rather is going to, whenever it realizes that there's a zero voltage being recorded, it's going to now discharge itself to give a portion of voltage, because you know that the diode stores charge. So it's going to discharge itself, and in the process of discharging, it's going to pretty much smoothen the full wave rectification wave. All right. There's a lot of things here that we must also consider. It says that when the output signal increases, right, the capacitor charge, because what you have to understand is that capacitors store charge based on the amount of voltage that is going towards it per se, right? So the more voltage you have going towards the capacitor, then it's the more it's going to store. You see what I'm saying? And it says as soon as the output voltage begins to fall, right, the capacitor begins to discharge through the load. And we're going to show you the diagram very soon. Now, a very important thing about capacitors. Capacitors have a thing what we call a time constant, right? And a time constant mainly for a capacitor has to do with the amount of charge remaining, right? Or pretty much the amount of voltage, right, that is remaining at a particular point, or in a sense. Because what you must understand about time constant is that to find a time constant for a capacitor is simply when 37% of the initial amount of charge is remaining, right? So let's imagine that we start out with 100 volts. Whenever the capacitor reaches at a value of, let's say, it's discharging. Whenever it's discharged and reaches a value of, say, 35 volts, then that is when we have recorded a time constant. But we know that we can also calculate the time constant. So rather than using the graph, because remember now a capacitor discharging graph look like this, right? So we have voltage, we have time. A typical discharging capacitor graph looks like this. So you start off with an initial amount of charge, 100%. If I wanted to find the time constant from the graph, then I would have to look to see what amount would be 37%. So I would go to find 37%. Once I find 37%, the time on the graph that corresponds to that will tell me the time constant. All right? So that's how we find the time constant using the graph. It's just when 37% of the initial amount is remaining. That's what I'm saying. But we can find the time constant if we know two things. If I know the resistor, the load resistor, and the capacitance of the capacitor, then I can know for how long will the capacitor take to reach 37% of its initial amount. You understand? Now, this is very important. The RC value is very important because what? Depending on the size of the capacitor, if you have a much larger capacitor, what it tells us is that the time constant is going to basically be much longer, which means that it's going to take a much longer time to discharge. You understand? So with a very high time constant, then your graph probably would look something like this. You understand me I say? It will look something much higher like this to say that, taking a much slower time to discharge or to reduce to 37%. That's what it really means. Now, if your RC value is lower, then it means that the capacitor is going to discharge very quickly, right? Which also tells us that it's going to reach 37% of its initial amount very quickly. Now, this is not completely related to smoothing, but it involves us understanding what is taking place here, right? Because this is just capacitors. Remember, everything that we learn ties in together. Good. So it's important to know that if you increase the capacitance, which is the C value, then you automatically increase the time constant. If you increase the resistance, you basically increase the capacitance, the time constant as well. If you lower the capacitance, you lower the time constant. So it just means that the capacitor is going to take a much longer time to discharge, which is something that you want whenever we're doing this. You want a very high time constant, right? Now, this is what you would have to do to your circuit if you want it to pretty much go through a process of smoothing. So the whole thing about smoothing, as we said, is when you would take a capacitor to discharge across the load resistor so that the full wave rectification wave can be more steady per se, to basically give you a more direct current. So this is what you would do to the circuit to modify it. All you would do is to connect a capacitor. This is the symbol for a capacitor. You would connect a capacitor in parallel with the resistor, right? And when you do that, what you're essentially seeing here is that this would have been your regular full wave rectification, right? With the broken line. Now, whenever you have the capacitor discharging, what the capacitor does is that it adds that portion of, some amount of voltage here. So rather than going to zero, it does not allow the voltage to go to zero. So the capacitor is discharging to keep some amount of current flowing so that the graph can now look like this. So at the end of the day, when you check it out, if you're really supposed to draw the graph now, then what you're now seeing is something looking like this, which is sort of more like of a direct current, because it's flowing in one direction. Even though it's going up and down, it's not going to zero. So that kind of make it be more direct, or it gives you a more steady flow. If you're going to zero and going back up to a high peak, that is not steady. All right. Now this is what we talk about just now. If you have a very large time constant, which is your RC value, which is the resistance times the capacitance. As you can see, the thick line right here is showing us that we have a very high RC value, which means that it's going to take a much longer time to discharge. So if I had increased RC to another level now, then what you could essentially do is to create another type of thing right here. So you could get an even more perfect, output. You understand? Looking more like this, to say that the thing is going to look more closer to the peak rather than having gone all the way down. You could use a much higher RC value and all of that to get a more steady wave. You understand? So that is just really what is happening here. All right. Now I'm going to leave this part for now. Right? I'm going to leave this part for now, the part that talks about how semiconductor works. So we will pick up on that part, but before we go, right, here is a question. You can take this question to try it, right? And then here's also another question. You could look at this question just the same way. And yeah,